Welcome to Lecture 8, Clustering High-Dimensional Data. In this lecture, we are going to first discuss challenges of clustering high-dimensional data. Then we will introduce methods for clustering high-dimensional data. Especially, we will discuss subspace clustering methods, including subspace search methods, correlation-based methods, bi-clustering methods. Within bi-clustering methods, we are going to discuss delta bi-clustering and delta p-clustering. We also briefly introduce dimensionality reduction methods. So for the first session, we are going to discuss challenges of clustering high-dimensional data. So why we have to cluster high-dimensional data? So the first question is, how high is high dimension in clustering? In our previous discussion, many examples we give actually only contain 1 to 3 dimensions. The most popular used example are just 2 dimensions for showing, for example, k-means, kernel k-means, EM algorithms. But these methods may not work well when the number of dimensions grows to 20. Not to say in many applications, such as text documents or DNA microarray data, if we take every keyword as 1 dimension in text documents, or we take every where in the microarray data sets, then we may need to handle tens of thousands of dimensions. So there are some challenges at handling high-dimension data. For example, there could be many irrelevant dimensions that may mask the real clusters. The second problem is the distance measure may become meaningless due to equidistance. We're going to introduce this a little more. Moreover, many clusters may really exist only in some subspaces. If you take all the dimensions into consideration, you may not be able to find quite meaningful clusters. Let's look at the curse of dimensionality problem. Usually, data in 1 dimension is relatively packed. It could be quite dense. However, when you stretch it into, say, 2 dimensions, then the data originally projected on 1D now become 2D data. It becomes more far apart. Then you add more dimensions, the data even become more further apart. So in the high dimensional space, the data could be very sparse. Actually, everybody may have such experience. For example, you watch the night sky on the dome. You probably will see there are some stars, some bright or some not so bright. They are very close on the sky, but once you really study, like use telescopes or ask astronomers, you probably know these very close stars in the real 3D space, it could be very far apart. Okay? That means the 2D projection you see is reasonably packed, but once you go to 3D, it may become pretty far apart. Then the distance measure becomes meaningless when you go to very high dimension, just because in dimension A, you may find these 2 is very far apart. In dimension B, it could be just noise or something. But once you see there are many, many dimensions, their differences could be you have data in this dimension, I have data in the other dimensions. And our measure, you measure is 1,000 as a unit, I measure only like 10 as a unit. So in that sense, in many cases, the distance measure may become meaningless. So some traditional data distance could be dominated by noises in many dimensions. Now, if we summarize the curse of dimensionality problem, there are 5 different aspects referred to the curse of dimensionality. The first aspect is optimization. That means when the data getting into higher and higher dimensions, then to do global optimization becomes more and more difficult. The complexity may increase, exponentially. So that's the reason, optimization may become a challenge. Then the second problem is distance concentration effect of the LP norms. The LP norms, for example, if L1, we just use the Manhattan distance, L2 is just Euclidean distance, we study this. But the distance concentration problem means far and close neighbors may have similar distances just because when the dimension is very high, their difference probably just on whether you have data in these dimensions or we have different dimension, we have different measures. So their relative contrast of LP distances could diminish when the dimension increases. That's a distance concentration problem. The third problem is irrelevant attributes. For example, you want to give a word to students. There are many dimensions could be irrelevant. For example, whether student height or student body weight or the student telephone number or student birthplace, those probably irrelevant for your award competition. So in that sense, if you put all these irrelevant attributes together, actually, then finally you may really interfere your real purpose of clustering, therefore impact the performance. The fourth problem is correlated attributes. That means in many cases, you get a subset of attributes, they may have strong correlation. Okay. Then if we take all the dimension is very high, but since they are strongly correlated, these sets of attributes can be represented by only one or two dimensions. That's a dimensionality reduction problem. Just give you a simple example. Suppose you want to give students awards. Maybe you want to look at GPA. Of course, you can look at every course, including their midterm, final, and homeworks. Many courses actually have strong correlation with their GPA. So you probably just want to look at their GPA or their major GPA instead of looking all those attributes. That means the intrinsic dimensionality of data sets can be considerably lower than the embedded dimension. That means the real number of features of the data sets. The intrinsic dimension could be like a GPA or the quality or the performance of the student. But on the other hand, the embedded dimension could get all the detailed on every course, their performance. Okay, so that's the reason you want to do dimensionality reduction. Okay, the fifth aspect for the curse of dimensionality problem is data sparsity. We already used the example to show the data volume in the high dimension space could be extremely sparse because in a very high dimension space, some may not even have a point because that point does not have that high dimension. Okay, that's a data sparsity problem. So those different aspects combined together, we can say this is really curse of dimensionality. We have to invent effective methods to overcome this problem in order to do effective clustering.